Hi, everyone. Welcome to C++ Russia conference. I'm Oleg Maslov. I'm I'm interested in the AI compilers and programming models developed, so I'm glad to be here. So worked prior to on the SYCL compiler, and really we are here to have a talk from a brilliant engineer. So let me introduce Abhilash. Hi, Abhilash, can you hear us?
Yes,
Yeah.
Здравствуйте, CPP, Russia, Oleg.
Great.
Good evening to
Okay,
everyone.
great. Yeah, hi. So Abhilash is from Intel, so he's one of the senior developers who stands behind the kind of development of a SYCL compiler. This is one of the interesting C++-based programming models for accelerators. And also Abhilash has a very good experience with open source projects like PyTorch, trying to enable this novel programming models and integrate to the open source, to neural networks. And today, so Abhilash will be talking and presenting the talk on the SYCL integrated compiler runtime for accelerator deep learning. So he's gonna talk about this, and this is kind of interesting to understand the modern novel approaches in this part. So Abhilash, hi. So let me just a few questions just to ramp up. So Abhilash, so what's the purpose of your talk? Just who's the
Yes.
target audience?
So for the target audience, it can be anyone who is interested in not only in deep learning but also HPC. The main agenda is you have to code only once in an accelerator language and embedded language, and it will be you can run it on every hardware backend agnostically. So it will be that much easy to run it on a single piece of code. If you're interested in parallelization of deep learning, not only in deep learning, but also in high performance computing, compute intensive kernels, and want to create only a single piece of code or a single source file which can run on AMD targets, Nvidia targets, Intel targets, other targets as well, this is the talk for you.
Great. So thanks, Abhilash. So you're about to start. So I will remind our audience. So we have a Telegram chat specifically for this. So feel free, and I strongly recommend to ask any questions in this chat. So I will try to moderate, and we'll try to answer most of these questions online. And basically that's it. So now stage to you, Abhilash. Welcome.
Yes, thank you, Oleg. So greetings. So today's talk, we are going to cover about not only LLMs and deep learning, but also about SYCL language and the semantics of SYCL in general, and how we are going to understand how to build different kind of models and different kind of kernels, and we are going to run it on different hardwares as well. That source code is going to be runnable across different vendors, different instruction sets, and we have the option to customize them as per our will as well. So it not only targets the GPU backend or the accelerator backends, but also CPU FPGAs. That is where the SYCL language actually comes, and we can show the true power of SYCL in general. So what are the contents that we are going to cover today broadly? So first, the scope of the presentation. Then we are going to have a brief introduction about the LLVM compiler backend and how the SYCL language actually comes into picture over there. We are going to have an introduction to the SYCL, which is going to cover the main part of the talk, the programming model, memory model, some instances of parallel STL, how it is different from the standard library, STDC++, as well as the adaptive CPP1 variant of SYCL. We are going to talk about a little bit about custom kernels, not only in deep learning, but also in performance computing with the PyTorch case study, if time permits, or else I will be in the discussion zone to discuss it. We have the DPCT toolkit for auto migration samples, how we are going to migrate automatically CUDA code to a device-agnostic SYCL code, which can run on different devices and target backends. Some performance results and references and conclusion. So the code is available at this open source GitHub repository. I will be taking reference from this code very heavily because I will be showing the code samples from there itself. Please feel free to take a look in the meantime. So firstly, the scope. What is and why do we need the SYCL language? The idea is to code once and build everywhere. right? So in the modern case, when we typically write accelerator codes for any kind of applications, the most prominent ones is CUDA. In some cases, it is HIP or AMD, but they are only device specific. What if we want to write a code that can run anywhere, right? So the SYCL language standards is such a way where we can write a compute intensive kernel, and we can create some different source files pertaining to different targets. Let's say SPIR64 generation for Intel, for AMD GCN targets, or for Nvidia PTX NVCC compiler targets, and we can run it anywhere. So this is where the cross-platform SYCL language comes into the picture. The scope also involves parallelism, because SYCL is based upon heterogeneous parallelism, parallel programming model. And we are going to talk some little bit about deep learning applications, and typically PyTorch. And lastly, the DPC++ compiler for auto migration of CUDA to SYCL code. So firstly, an introduction to the compiler backend. We all know that the LLVM compiler is like a standard industry-strong tool chain for different kinds of compiler standards for converting different kind of source files to different LLVM lower assembly files. The SYCL language is built upon one of Intel's proprietary compiler, which is known as the DPC++ compiler. SYCL language is one of the proponents of that. In Intel, we have three different compilers, which is ICX, ICPX, and DPCPP. We'll be looking at ICPX very heavily because that is the command that we'll be using to compile SYCL codes in general. The linking and all of this is done by the standard LLVM standards. So LLVM standard linkers, code linkers, and everything remain the same. So this is the prototype how it happens. So we write the SYCL code, source code. We use the LLVM or the ICPX or the DPCPP compiler to convert that source code into different LLVM standards in bit codes, and then we have the device-specific runtime lowering of that. This is a generic flow. What happens in a typical C++ code? We have the .bc format, LLVM bit code, and we can use the LLVM bit code, which is highly optimized for different loop unrolling and other optimizations to convert to different targets. And this is the overview of how the Intel's compiler uses the SYCL code for generation of fat binary files, which is the end product. So we have two components in the SYCL code. Typically, one is the host and one is the device. So the host one is done by the standard C++ compiler. The device part is done by the SYCL backend compiler, which is the DPC++ compiler. We have to specify certain link targets as well through the LLVM linker. In this case, for Intel, it is LLVM SPIR-V because our hardware's target SPIR generation from Khronos standards. For Nvidia, it is the PTX or the SM streaming processors target for Nvidia. And it will have a similar kind of an architecture down the line. So after linking, it goes down to the compiler and links to produce a fat binary file. So before we start off with the coding part and understanding the core semantics of the SYCL code, let us understand how we are going to run a particular SYCL code. The most important and the fundamental command is this command, ICPX -f SYCL, your source code and the output, how it is going to be. Okay, so here ICPX is the compiler if you are using, if you are having SYCL language in general. If you do not have the ICPX compiler, you can also use the clang++ compiler. But in that case, you have to specify the STD C++ standards to 17. The reason being, Khronos 2020 SYCL specifications state that it has to be with the C++ 17 standards. For SPIR-V builds that is targeting to the Intel kernels, you can have this kind of command. You see the ICPX fsycl device only. This flag indicates that it will be compiled only on the device, not on the host. And if no use bit code, you have to pass in your source code, and let's say the output is going to be in SPV format, which is your Intel format. Let's say if you want to target for Nvidia backend, the same source code which you have written in SYCL, you want to target for the Nvidia backend, the command is going to be just simple. You have to just pass your fsycl target or your xsycl target. So both these options are available. You can pass in fsycl targets or xsycl target backend, NVPTX64, Nvidia CUDA. This will help your code to get compiled for the CUDA runtime. And then you can use your LLVM disassembler and do all of your codes when you have the bytecode format as well. So the rest of the functions are pretty much straightforward. You are replacing ICPX with clang++, and just like I said, these are some of the ways you can compile your SYCL code. Some important features of the compiler features for ICPX, typically, it provides AOT so that you can have your target machine typically suited before your runtime, so that it gets compiled previously before even going into the device-specific compilation stage. So we will be seeing another example of a particular open source project called as Adaptive CPP or SYCL, where there is a single pass compiler in that case. Here, AOT is a typically very useful case where you have a single source file and you want to already have designated targets where you want to compile. In this case, I'm targeting for the AVX2 instruction set sizes, and XSYCL target backend is this. This is for the CPU case. The XSYCL target over here is x86 architecture with 64 bits of SPIRV. Similarly, if you want to have Nvidia, you have to change it with the Nvidia targets. There is also one other option to link separately, so host and device output files. So in this case, you have your normal host code, you have your device code compiled separately, right? Kernel code, which is a device code, you can link them directly. The two source files, you can link them directly. So this also option is available in the case of AOT for ICPX compiler. Now let's get into the core of the SYCL language in general. So the SYCL language has two main components. One is the host code and one is the accelerator or the device code. This accelerator can be CPU, GPU, FPGA, or any other accelerator, right? So, and the important concepts of SYCL is mainly three parts. One is the memory model, one is the programming model, and one is the parallelism. In case of the memory model, we have something called as a pointers or the buffers. For the programming model, we have something called as queues, which are also called as command queues, which are called as task orchestrators. That means they are orchestrating all of the threads, pools, and everything inside SYCL. And the last one we have parallel for, which is the heterogeneous component for induced parallelism in SYCL. This is the SYCL ecosystem in general. We have seen a little bit about the compiler backends of Intel, and in general. And we also have the compute CPP backend from CodePlay, and we have the HIP SYCL, which is now known as Adaptive SYCL, which we'll be looking into as a case study, minor case study. So it is a very big ecosystem from the SYCL standards. So let's move into some of the core concepts. So the first important concept or the list of concepts is unified shared memory. So this unified shared memory is a typically broad use case because it deallocates memory from the heap. So and it enables codes with pointers to work naturally with buffers and accessors. So this implies that whenever you're writing code, in the case of SYCL, we'll be seeing in the examples, there are different cases how we can use the shared memory. Whatever containers, let's say data structures we write, it is going to stay in a memory a little bit more longer than some other counterparts. The reason being that it not only we have the scope of not only running it on the host, but also deallocating it to the devices, and also allocating back to the host, as well as keeping it in a transient shared memory. We'll be looking at it more in after certain slides. We also have certain thing called as parallel reductions. There are many kind of parallel reductions, which is the core concept of SYCL heterogeneity. We have parallel reductions in terms of worker groups, threads inside of work groups and subgroups and so on. The next is work groups and subgroups. These are some nomenclatures which are given to a group of collection of threads in the SYCL runtime. It is almost semantically similar to the Nvidia CUDA blocked architecture of memory, but there is certain differences. Think of subgroups as a collection of threads and the work groups as a collection of subgroups. So this, and all of them work asynchronously. We have CTAD, which is the class template argument deduction, as one of the vital features of SYCL. We have another memory model apart from USM, which is known as accessors, which is actually a volatile memory and used for dynamic and built-in reduction operations. So any kind of group operations, or let's say shuffling, reduction, any kind of group reduction operations, let's say group numerical operations is very much important. Accessors are actually transient and very volatile. That means they stay inside your device code, and as soon as you go out of the device code, you have to write it back again into the memory. So then you have the standard C++ atomics, which is from where the SYCL standard C++ atomic ref is actually taken in looking at it in depths, in certain cases of this. The first thing is memory management. So like I said, there are two kinds of memory managements. One is through the unified shared memory, USM, and the other one is through buffers. Buffers are actually the transient memory stage, which is through accessors. And the unified memory is like one of the where we use a kind of C style coding where we use malloc and everything, which is a pointer based programming model to allocate and deallocate let's say containers, data structures from your host to the device and so on. We have to be very much alert when we write USM code, because in many cases your code might run out, give compile time or runtime errors. The reason being your host allocation is the device, but you have not back transferred it from the device to the host after your kernel gets executed. So it is very important to keep that in mind before. We are going to see a lot of examples on this. Buffers are powerful and elegant. Mainly in your application. The buffers aren't disruptive to your development. USM provides a lot of pointer-based C++ interface, but USM is not generally used for performance. For performance, if you want to use any kind of group kernels where you want to have asynchronous threads running different kind of compute-intensive kernels, accessors are the one, or the buffers are the one where you are going to use it. So explicit, there are two kinds of scheduling, which happens. So one is the explicit scheduling, one is the DPCPP graph scheduling. Explicit scheduling is what happens when you are having queue, right? And we have not learned about this queue part just yet. We are going to look at it a little bit later in the examples. So here, buffer task queues are entrusted with having a queue, which is a centralized orchestrator, right? And it is going to pass in your data structures, let's say int or whatever it is there, int, float, whatever data structures you have on the host to the device for the runtime. Here, if you see very clearly, this is actually the structure of how the SYCL code generally is written. I'll be coming into that later a little bit depth, but you have a queue which submits, which is actually the command queue which submits your asynchronous task or asynchronous kernel in a kind of in a lambda manner. And then you have, let's say, you have a transient variable. So this is inside the kernel. So this AutoVAR is inside the kernel. So it is very transient. It will not exist outside your kernel scope. That means outside the queue scope. And this parallel for is the third important component that I talked about, which is the main component or the lambda, where you are going to actually perform your SYCL kernels. We're actually going to write any kind of computation kernels, let's say addition, subtraction, or any kind of compute kernels. Here we see another example of it. Let's look into one example of SYCL in general. So this is how the SYCL queue looks in general. This is the prototype of how the SYCL queue looks in general. We have a queue.submit, right, where we are submitting a queue. We have an accessor. So here you're using an accessor model, buffer model, not a USM model. And then we have a parallel for scheduler in Lambda mode, because Lambda is by default the de facto method in SYCL. There is also function point kernel functions. We'll come to that later. But Lambdas are the most popularly used way of writing the actual code inside the SYCL kernel. Now I'm going to switch to an example mode to actually show you what a SYCL code is and how you're going to write it. Let me just exit from here. And let me switch to an example. So let's say I took the GitHub because due to technical difficulties. Let's say this is one of the SYCL. This is from the compiler conference GitHub repository. Let me zoom in and as well so that you can take a good look. Here we are going to understand about parallelism and how to write a queue as well. So we have something called, firstly, we include the SYCL headers and the DPCT headers if needed. We initialize a queue, which is an in-order queue. We get the device, we get the context, right? And let's say over here, in this case, we are creating a malloc pointer, malloc shared. Malloc shared indicates that it is in a transient memory space, which is both on the device as well as in the host. Here we have a typical simple SYCL kernel, which is a parallel for scheduler, where we take the this data structure and we are incrementing it at each time. So this is a simple parallel for without any kind of one-dimensional parallel for. So we have another kind of parallel for which instantiates a class. So this is how we can also instantiate a class in this case, template class. This is another this is another kind of a kernel which is a single task kind of parallel for, which is only having one task, that is one thread is running on it. In this case, only one work group is having one thread. Over here, only one thread is running. So there is no concept of work group in this case in a single task. So then you have a parallel for for other variants. One of the interesting variant is this one. So we have, just like I mentioned, we have work groups and we have work items, that is the subgroups, right? So we have the capability in SYCL to also write parallel fors for each of the individual items. That means we can schedule a parallel for work groups as well as work items as well. So here, this is a diverse case of a parallel for or a asynchronous scheduler, where we are submitting a queue, which is a task queue, which on a work group, right? Work group containing of subgroups. And this is a two-dimensional work group, which is there, right? And here we have a transient, or I would say a device-specific container of memory or a variable. And then we are scheduling a parallel for each work item. That means each thread inside a particular subgroup. So here we are doing for that each thread which works asynchronously, we are performing some arithmetic operations. We are getting the IDs, and we are getting, we are multiplying 2 for each ID. We'll get to these nomenclatures a little bit later, but this is how in general a particular SYCL architecture looks like, or a parallel for with queues looks like. Let me go back to another piece of code in general, so that you can take a look in details. So for instance, let's say this one. This is a sample example which loads, which takes two, I would say, buffers, which takes two buffers, A and B, computes the addition and stores it in a third buffer, which is C, right? So here you have three buffers, right, over here, which N and M, two-dimensional buffers. Here we are specifying an accessor mode. That means USM mode, in the accessor mode, which is actually in transient, which stays only in the kernel. So this accessor A is only write, so it does not have read. So here what we are doing, we are filling the A buffer index-wise with certain values. Okay, this is a simple work group, which is a parallel for that we have just seen another example. And then we do a similar asynchronous kernel launch for B. We also want to fill the B with write only parameters. So we are, in this case, we also scheduling a parallel for B for each index of parallel for which for each thread. Actually, in this case, we are filling in certain values. And here you see an important aspect called as wait and throw. That means a synchronization primitive. We'll come to synchronization and border fencing after some time. But synchronization is very much important when you have a use case like just the example I showed before, where you have work group parallel force as well as work items or subgroup parallel force. You need to have some kind of synchronization so that the threads do not run into or interfere with each other, right? This is typically the standard way that we have learned so far how to write a SYCL particular kernel. And let's say we now have another kernel where we compute the addition of A and B, and we make C write only, and in this case A and B are only read. So here we are going to read the values from A and B, perform an addition, and we are going to create a accessor or a device accessor which is write only. Over here, you see the parallel for schedule over here, C index equal to A index plus B index. That's it. That's how you're going to write a simple kernel to enqueue a parallel kernel writing on an N cross MD 2D iteration space. And that's it. You can just print the values and you can just get the output as it is. So this is how you normally write a SYCL kernel with the command queues and everything. Let's go back to we have learned a few of the nomenclatures. One of the nomenclatures is that item.getID. So for example, if you see over here, we're going to look into that shortly. So for instance, that was in the previous example. Let's say SYCL parallelism. So the output files are also there for your reference in this particular code base. So you can just take it and run it. So for example, this nomenclature, right? What is get global ID and what are these kind of, we have learned about the parallel for, we have learned how to write a SYCL queue, but what are these intrinsics? We are going to learn about them just now. So let me reshare it back from the current slide. So now we have just seen the example of this case, right? How we are going to write a SYCL kernel. Now let us move back to a few use cases of memory, right? Now you might have noticed that in some cases I have mentioned that you have seen malloc shared in the examples, right? So it is one of the USM memory parameters where we specify a kind of shared or a transient memory space which exists both, where a container or let's say a data structure exists both in the host as well as in the device. You do not need to manually transfer it from the host to the device. We are going to see an example where we manually transfer, but in this case, let us assume when we write malloc shared, it is not going. You do not have to do that. This is the aspect, SYCL aspect of USM device allocations and USM host allocations. Generally, when you write malloc host or malloc device, you are going to get device specific or host specific data structures there and then and there. Okay. So we have seen how to write the SYCL queues, right? Command queues. Now let us know about them in general. So DP++ queues or SYCL queues in general are out of order queues. They are directed acyclic graphs. You can also link the output of one queue, that means one kernel, to the input of another kernel as well. So that is also possible in this case. Okay. And so here you can see the linking is happening over there. So auto f q submit h dot depends on e. This means whatever output is coming on e is going to be used and interpreted in this particular kernel, which is f. And same thing happens over here as well. So it is a kind of a DAG, a directed acyclic graph, where you can link out of order kernels in general. But in order kernels are actually more easier to do. You can also specify the kernel mode as in order, dpctq in order. We have seen that in the example before, the first example, but also you can manually specify it as well. So now let us look into we have seen the programming model in a nutshell. Now let us look into the memory model of how it happens. So in case of SYCL, we have a 3-dimensional memory structure, which is known as ND range. This ND range is when you write a SYCL kernel, you are going to, inside the parallel for, you might have noticed some lambda notations where you are specifying SYCL range 1, range 2, range 3. That range is known as an ND range. Okay, this ND range is like a 3D architecture or a 3D memory pattern, which is made up of work groups. Each of those work groups are made up of subgroups, and these subgroups have individual threads, which are known as work items. So all of the work groups run concurrently. They may be scheduled to run at different points of time. So synchronization is upon the, by default, SYCL manages synchronization in its own through ND range memory fences as well as buffer memory fences. But also you can also manually specify synchronization, just as the example we saw, that wait and throw, q dot wait and throw in the previous example. So the index space is divided into ND range, and work groups, subgroups, are the main constituents of that. So the next important aspect about the memory is what kinds of memory are there. In the USM aspect, we have seen about host, device, and other variants of memory. So we have the global memory, we have the local memory, private memory, and the generic memory. Global memory is across all our work items, right? USM allocation, 2 or more work items scheduling. Local memory is across individual memory groups, subgroups. Private memory is a region where the memory, attempt to access private memory is actually very much trivial, because you need to have synchronization in place just in case, because it may give you undefined memory behavior. You also have a generic memory, which is a virtual access space, which overlaps the global, local, and the private access spaces. So there is a minor difference between local and private memory in the difference being that in private memory you need to have specialized accessors to access that particular aspect from the memory. Subgroups, we have already seen what subgroups are. It is a collection of a particular group of threads inside a particular ND range or a work group. So we have seen a particular example. Now let's see another example, as mentioned over here. The task of this SYCL queue or this SYCL queue is, or this SYCL kernel, is to fill every value with 42 in this 2x2 in this 2-dimensional matrix, for example. Okay. So here the parallel for has something called as ND range, which is 2x2. We are specifying the work items, which is a lambda. We are filling the values of the IDX with 42 for each values. This is an accessor, which is write only. So the same pattern, what we have seen in the examples. This is another representation. As a norm, we specify the work group size as multiples of thread size into the subgroup size. By intrinsically, it is the SYCL is SIMD compatible. So whatever work group size is going to be, it is going to be the work items multiplied by work items or threads multiplied by the subgroup size. So just like the memory scope I talked about, the memory scope for the global, local, private, and the generic are also divided into work group based, ND range based memory scope. So we have something called as the memory scope, called as the work group memory scope, subgroup scope, work item scope, as well as the system and the device scope. The outer one is the system, which is the broader, or I would say I would say that the global memory, and these are all part of the local memory. So the work group is actually part of the global memory. The subgroups and work items are actually part of the local memory and private memory. So now the next important part of the SYCL kernels is about task and hierarchical parallelism, right? So we already saw this example in the previous case. What is a parallel for work group and as well as a parallel for work item? As I said, that there are two kinds of parallelism as before in the case of SYCL. One is task-based parallelism and one is hierarchical data parallelism. So when you schedule a parallel for, by default, it goes to the ND work group or the ND range. Then you have a hierarchical parallelism where it is for the individual work items. And then you have a synchronization where we are specifying q dot wait and throw, or normally q dot wait. Now let us look into this vocabulary that we have seen a little bit before. So the first one is get group ID is the ID of a work group. Get local ID is the ID of a work item in a group. Get local range is the dimensions of the work item. Get group range is the number of subgroups inside a work group. Maximum local range is the maximum number of work items permitted in a work group. And the rest of them are just interpreted as the group ID or the local ID with the first array index, right? So these are actually the important parts. You will be seeing this in some of the more examples where we are accessing each of the individual blocks, right? Now, before one of the interesting things about this is you know understanding about kernels. Generally we see lambdas in the case of SYCL, right? We generally see lambdas in the case of SYCL, but in the case of there is also another pattern of kernels as writing as function objects in the case of SYCL. That is also there. In this case, we overload the operator. This operator we overload, and member function must be const qualified, and it must take some traits. Okay, we'll be coming to traits a little bit later, device copyable traits, and it may take different parameters depending upon the data accesses for the specific kernels. For example, this is an example which is also there in the case of the open source repository. So random filler is a class which takes the random distribution, and over here we are overloading the operator, const operator, to get for each ID. We are calling the get random function, which creates a normal distribution. The uniform distribution. And here, instead of lambdas, we are not calling a parallel for over here. We are just calling the function or the class object directly over here, and it is overloading. Since it is overloading the operator, this operator, it automatically calls this get random function, which is an intrinsic function inside the class member function, and it gets, or I would say, a constructor function, and it gets called over here. So this is also another way of writing SYCL kernels apart from lambdas. The parallel for is ensured in this case. Kernels as lambdas are the most popular examples that we have seen today as well. The next thing is the device copyable traits. This is by far one of the core concepts of SYCL, which introduces that whenever you are creating a device, whenever you are creating a data structure that is going to be going inside the kernels, right, either through USMs or through buffers, it is mandatory that when writing the buffers, you have to make sure that your data structure is device copyable. So it has this, whenever that means whenever whatever template type name parameter is going to be at the top of that particular parameter, it is going to be copyable, and it is going to return true for that particular value. Is device copyable must meet the C++ 17 unary trait requirements. That if in any case is device copyable, this template type trait is false, then in that case your kernels might give compile time errors as well. So by default, whenever you write your SYCL kernels through accessors, buffers, images, streams, IDs, ranges, ND ranges, arrays, and vectors, by default, all of them follow this type trait by default, device copyable type trait. There is another type trait we'll be coming into, which is known as the group functions. So like I said that at the before, that accessors are typically very much useful for device device specific or group specific reductions or group functions, right? So in this case, we have a type template type which is known as isGroup. So isGroup is a template type trait which helps you to perform different kind of operations. So broadcast, barriers, group algorithms, any of all of which are also there in the standard C++ ranges as well. Shift permute, everything is supported here as well through these group algorithms. So this is the template type name in this case. So you have the const expression bool is group V, which interprets to true always, provided you are using accessors in this case and writing the SYCL kernels in the way that I mentioned before. So for example, this is a group barrier, which is like a memory fencing barrier I mentioned about. So here you're passing the group, that is the ND group or the work group, and the memory scope, fence scope, which is the group fence. So that means it is creating a global barrier, not just a local work subgroup barrier. It is creating a global barrier. So this is one of the example which uses the type name type trait group. So another important thing, concept about SYCL is address spaces. We talked about memory modeling, right? We talked about global memory spaces, local memory spaces, and all. There is something called as pointer class, which is most important in accessing accessors. Where what address space are going to be in, whether they're going to be in device, whether they're going to be in much smaller memory space than device. Let's say transient memory space, which is generic, right? So DACC is kind of like a accessor, right? Just like we have seen in the accessor examples, write only, read only, it is similar to that. DACC is a write accessor, DA, and we have something called as a multi-PTR attribute over here as well, similar to C++. We have an explicit pointer class, global PTR. We have a generic address space, which is SYCL external. When we write SYCL external to an intrinsic kernel, right, it implies that it is going to be in generic address space, right? So let us look, and the last, typically, I would say the important part about SYCL is, I would say, exception handling. You have an exception handling in SYCL. It generally means that this is how you are going to write it. So you have the SYCL context pertaining to a particular device, device context, and you are going to catch an exception, and you are going to get an error, throw the error code. So queue, wait and throw, asynchronous, event, wait and throw are some of the other samples as well in this case. So just like I mentioned over here, this event, wait and throw is dependent on a context as well as a device. So continuing on from the previous slide, here we have a device event class, which also is used for synchronization. So this device event has only one function, which is known as a wait, which prevents your kernel from, which provides a synchronization block. Atomic refs are similar to the SYCL standards in C++ atomics. So we have the atomics in this case for memory, different kind of address spaces. It is slightly different than the C++ atomics in the sense that over there the memory pattern or the memory alignment is known. Here you have to specify the memory ordering, right? Whether it is going to be in generic memory, local memory, private memory, and so on. So this is the template parameter for the atomic refs. Some metaprogramming things which we have already seen. Metaprogramming means that you have to power of C++ generic programming or templated programming. It also provides the operator overloading parameter, where we have already seen in one of the kernel as object functions example. Now, one of the important things about SYCL and CUDA, right, where CUDA comes into the picture, right, CUDA SYCL. So CUDA has almost a similar kind of grid architecture compared to SYCL, but here we have thread blocks and grids. Grids are combination of thread blocks, okay? The mapping is like so. So if we have, whenever you write a CUDA accelerated code, you are going to have thread idx.x, grid idx.x, block idx.x, block dimension idx.x, right? So you are going to have different kind of XYZ 3D parameter. It is switched in SYCL. So X represents 2 in SYCL, Y represents 1 in SYCL, and Z represents 0. So the corresponding translations are like so. So group range indicates grid item. Block dimension is local range. Block IDX is get group, thread IDX is get individual local ID, and warp size, which is another parameter in CUDA, is represented by get subgroup, get local range. So you are getting the first local range ID for that particular subgroup. So this is just a nomenclature how when you will be seeing an auto migration. Similar things in so this kernel, when you use the DPCT toolkit, you are going to migrate it to this particular SYCL queue. So for this CUDA SYCL as well, you are going to have, while building it, like I said, you can specify the FSYCL targets for Nvidia and CUDA as well. So the CUDA driver needs to be present. NVCC, it has to specify that SYCL backend ext one API CUDA. you can make a check in your C++ code to make sure that the CUDA accelerator is present for your compilation. And this is the composite code, or I would say the command for running a code SYCL app for your AMD Nvidia targets as well. Okay, including SPR64, right? So the executable targets. Now, some implementations of parallel STL is that one DPL is Intel's version of parallel STL. So if you see the example over here, this is how a normal C++ code gets written. And in this case, you have the parallel STL implementation. So you have the one API DPL executor where we are performing different kind of ranges, execs, and different kind of STD operations. We'll be coming into that a little bit depth. So one DPL or parallel STL for Intel, which is there in SYCL, is for random accessors and iterators are provided. Function objects are passed to algorithms for the const qualified. There are certain differences in the sense that the function objects are should be const qualified. The SYCL says that writing an object is undefined. So we support majority of the STD variants, including STD exec, STD ranges, as well as asynchronous behavior. So let's for example, let's look at an example of composite example for the showcase, right? So over here, let me just let me just zoom out for a bit. So parallel STL. So let's look at this aspect. So if I look into this, so this is the DPL, the parallel STL for SYCL DPL. So you have the STD exec where you are calling STD fill. Now you know that STD exec has execution has different kinds of parallelization. So you have unsequenced parallelization, you have sequenced parallelization policy, and different other policies as well. So here we have an unsequenced parallelization policy where you are passing in data and filling the data vector with 42. There is also similar kind of experimental for the STD ranges in C++. We have the SYCL buffer where we're adding it data from the these arrays. We have views. What view we want. So let's say we have all views. This is actually similar to the STD copy view in the case of standard library. We have the iterator, which is almost similar to the STD iterator. This is an example showing how to create a counting iterator, right? So counting iterator as well as a transformation iterator, where we are creating an array, right? And we are alternating the sign from plus to minus for each individual elements of the array. All right. So you will also have a counting iterator. So here in the next example, we see something called as STD reduce. Similar to STD reduce, we have the reduce async. Different features are also there. So transform async, fill async, which is also there in the standard template library. This is a collection of the different items in parallel STL. And there is also a kernel written so that you can take a look. So let's say this is a kernel for swapping two vectors or two buffers, right, using the standard template library. So here we are creating a SYCL buffers, right? We are creating the SYCL buffers in this case. We are creating the device queue, range, a number of items. And in this case, inside the actual kernel, right, kernel's swap kernel, we are calling the one API DPL swap, which is almost similar to STD swap. Okay, and the rest of the code part is almost similar to the semantics that we have already known. Yeah, you can run this function and you can get the results in that case as well. Okay, now before I move ahead, I want to share this as well, which is the compiler explorer. The link is also there in the slides. So here we see an example of USMs, hopefully in this case. Hopefully, yeah. So here I think you are going to have something called as a queue, SYCL queue, and you are going to get the corresponding, the assembly codes, x64 and the SPR64 assembly codes as well. This is for one of the examples, which is known as block reduce, which is a customized kernel. So I will be coming to that a little bit later, hopefully, but in this case, I'm just showing it here just for reference. So the block reduce kernel is using the buffer accessor USM buffer accessor model, right? So here we are calling the SYCL queue as it is, and we are calling a block reduce kernel. Now, if we go into the block reduce kernel reduction, here we are doing something called as a summation reduction. That means we are adding the values of the input buffer, and we are getting the output, right? So here we are getting the local ID for each item. So 2 means X, thread IDX.X in the case of CUDA. and output, we're getting the output, and we are calling reduce over group, which is a SYCL primitive for calling group reduce operations for addition, right? So you can run it on the online compiler, and you can also get the results. So this is one of the examples of the parallel STL library, and yeah, so just like I mentioned, it links with the execution in a parallel unsequenced policy for this particular example. So ranges, views, all. So for example, we also have iota view, std iota view, as well as reverse view. So this is how the prototypes, how you're going to write it. We also have the reverse one that I talked about. We also have the link with std iterator. So this is, for example, a counting iterator where we were adding the values of the individual buffer. Here we have a swap, the example which we saw just now. And let's move to adaptive CPP, which is just a small case study. It won't take, I think, much time. It is a highly good, I would say, open source SYCL platform, which provides single pass compilation and also multi-pass compilation. So this is, so in the case of adaptive CPP, if you are going to run with the SYCL runtime, you have to specify minus minus a CPP targets generic. This will create a host level binary file which you can AOT to further device primitives. So let's say NVPTX or SPIRV or AMD, it doesn't matter. So this is how it happens. So CLang based SYCL code or the SYCL code. The host pass, this is where the ACPP targets generic comes into the picture, unified code base, and then you can JIT it to your particular host file, device specific runtimes IRs, or you can AOT to your specific device specific runtimes. So this is where the adaptive CPP open source repository becomes very much important. It is also linked with the std parallelization library, std transform, std replace copy, std for each. I think most of the std standard template, C++20 standards of ranges, parallelization are included in that particular scope. So these are transform, replace copy, and for each. So you can leverage C++20 to certain aspects in this case. The example I talked about the CUDA code. This is actually the corresponding CUDA code for the online compiler, which I talked about. So the SYCL code, which I showed in the online compiler for reduce over group, this is the CUDA code, how it looks like. You can see almost semantically it is similar. So thread idx.x converts to the local ID2, as we learned. And the block. So I think, yeah. So we have another sample called as a softmax activation. This is a deep learning example. I can discuss it more in the discussion forum due to time limits, where we are applying deep learning kernels and how we can modify them. These are very complicated kernels of CUDNN, right? We have the corresponding translations. And let's move into the DPCT, the last part of today's talk. DPC++ auto migration toolkit helps you to migrate CUDA code to SYCL code in very easy manner. Okay, so the central command for using DPC++ is this particular command, DPC++. You have to specify your CUDA include headers path, and you have to specify your in root containing your DPC++ in your CUDA code, and the out root where you want the DPC++ or the SYCL code in general. So these are the steps for building the Cyclomatic or the DPC++ compiler for Linux systems, as well as there are for the Windows systems as well in the repository through Ninja. And this is only the generic command you can do to convert all of your CUDA code to your SYCL code, right? So you have also inbuilt or user-defined migration rules as well. So let's say, for example, whenever the CUDA code detects something like force inline, it is going to migrate to, let's say, only inline. So here, the in file, whenever it reads force inline in CUDA code, it is going to migrate to inline in the SYCL code, and so on. So user-defined migration rules helps you to migrate some manual AST, right, to a SYCL AST, which is supported by the SYCL or the DPCT compiler. And that's it for the performance numbers relatively, SYCL code versus CUDA code in general. So we have seen a lot of performance in case of SYCL and CUDA. The higher, which is in this case, is better. These are some workloads which are compute-intensive HPC workloads. Similarly for AMD HIP as well as AMD GPU, AMD SYCL on AMD GPU. Some parts of adaptive SYCL is also over here in this case on the or HIP SYCL. And this is one of our internal I would say external benchmarks for the Intel benchmarks on the particular deep learning model of Llama 3. And yeah, so the resources, everything is present over here for the codes for the talk, as well as whatever samples I took, including this is a centralized repository which contains even the DPCT migrations as well. I think that's pretty much what I wanted to cover. And let me just go back to just DPCT, one example of DPCT to show you how this migration looks like. So let's say we have this live example where we have as the CUDA kernel, which is a simple CUDA kernel in this case, right? Okay, it's hello CUDA kernel, right? Just accessing the blocks, doing nothing, just showing a print statement. We have CUDA mallocs, we have memset. So it is going to translate to DPCT malloc, SYCL DPCT malloc, or DPCT DPCT malloc, right? So here, this particular kernel is going to get migrated to this. This is how the kernel gets migrated in DPCT by default, right? When you trigger this, and the command for running this is present at the top of the code file. So you have the DPCT format range none, USM level, these are optional. Outroot, the CUDA include path, the CUDA headers, and the CUDA host only or CUDA device only will trigger for the host or the device specifically, right? You can use the specific commands and you can get this output. The output is also provided to you in the DPCT output file. So you can see the output files is going to be in this dp.cpp format. You can convert it to .cpp format as well for simplicity, but means the same. So if you look at this particular code file, it is going to have this group this kind of format from IDX block dimensional.idx. It is going to have DPCT malloc. It is going to have the ranges and the parallel fors and so on. So and there is also an example on the user-defined migration. You can take a look, and I'm also there in the discussion forum for the time being. And let me go back to the final concluding statements from the slide. That's SYCL and DPCP provides tools for writing high-performance parallel programs, not only for different accelerators, but also for HPC and other stuff as well. This is understood. We are understanding how to write a SYCL code in generic to avoid bugs, as well as using the DPC++ compiler to auto-migrate SYCL code. We have learned some aspects of STL where the C++20 standards are trying to come into the picture through ranges, execution, in some cases boost and other aspects in C++, in parallel STL, DPL, and in some cases 1DNN, and lower level tracing and profiling to debug and optimize the program. And yeah, that's pretty much that I wanted to cover. And I'm open for questions if time permits.
Okay, thanks. Abhilash, yeah, that's was great presentation. Thanks much. So very packed, a lot of information. So yeah, I have thanks from the chat writing. So for the discussion, maybe let me start. So first question. So just packed information, a lot of information, but like a summary. So again, who's the target audience? So I mean, who should use this in which cases? So just let's make it kind of clear. Yeah.
Yes. So people who like single-threaded programming, they should not they should not have been in this talk. But people who love multi-threaded heterogeneous parallel programming and who are interested in lambdas in lambda format, not only in lambda format, but in C++ way of writing kernels, device-specific, accelerator-specific kernels, which are portable across devices or across vendors. So the code example that I have shown just now are all runnable, compilable for different backends. So you take this, let's go back to this any kind of example that I talked about, right? There are lots of examples in this repository. So block load, block store, quantization examples, convolution examples, attention kernels from deep learning, as well as different kind of smaller kernels are there, right? Including softmax matrix multiplication kernels. All of them can be compiled on your NVPTX targets, can be compiled on AMD targets with the command I showed you using the same code. So you do not have to write your code again. So use those binary files, output files as per as your wish. That is, and use the flexibility of some of C++20 standards using parallel STL, right? This is very much important for if you want to speed up through STD execution and probably through STD ranges. If you want to perform reverse filtering or other kind of operations, off and time, it's very much useful. So yeah.
Okay, great. So let me check. So and maybe another question, since we are kind of on the C++ conference right here. So people may have a question. So, and this SYCL is totally very much C++ oriented and uses a lot of things. So, Abhilash, so is there any plans when this can become a standard? I mean,
Yes,
in the
this
C++.
is an excellent question. So we are in talks with the standard work group committee. There are some evolutionary work groups as well as some work groups where we are trying to advocate for SYCL adoption. Since SYCL is the only hardware backend which embedded device accelerator language, which is cross platform specific. It can run across different platforms. We have got a lot of support from a few of my colleagues as well as members outside SYCL, let's say Adaptive SYCL, who are the creator of Adaptive SYCL, TriSYCL, and other open source repositories, all mentioned in the resources in the slides. So so the thing is, since SYCL 2020 standards is heavily embedded in C++17, we hope to have migration to the more advanced CPP standards. Slowly, 20 and 23, the more new features of reflections and everything is going to hopefully come in. And we are in conversation to see how that adoption takes place with the work groups. Yes.
Okay, great. Also, yeah, okay, thanks. That's good to hear. So that's the conversation is ongoing. And still about you mentioned the people C++, right, who is interested in parallel. So, but C++ suggests some other models. I don't know, parallel STL, I don't know, TBB. I mean, not C++, TBB. There are other libraries to make the things parallel. I don't know, even OpenMP. So, what should be? Why SYCL? Why SYCL? Why not some other things?
So it's an excellent question. So the parallel STL examples which I just showed you, two small examples, or using one DPL. So one DPL intrinsically uses one TBB or one thread binding blocks synchronization in general. So when you use for example, in this case, when we use the experimental ranges scope, right, it intrinsically calls your one TBB headers. So it's for synchronization and calling all your compatible execution headers or ranges headers like that. When you are writing the SYCL code and when you're using the DPCT toolkit, right, it will auto migrate your standards of your SYCL code of your CUDA code, right, to your one DPL, which is internal parallel STL for Intel, to that particular standard. It is also an open source repository, an open source standard, and that will use by default 1 TBB power. Okay. Due to shortage of time, I did not cover 1 TBB in general, but 1 TBB and 1 DNN. I'm there in the discussion forum for that, but it intrinsically calls that. OpenMP offloading is one of the important topics which is already supported in the DPL and parallel STL for Intel. So OpenMP offloading is typically a little bit faster, I would say, than the standard implementation of STD. That means the C++ standards of 20. And I think it is there is also one of the features which is there in the case of parallel STL as well. Yeah.
Okay, cool. Okay, I think we still have some time. So I'm curious about, okay, so we talked about this nice thing, so why SYCL? So, but many developers could care about one of the first priorities, stability of the
Stability,
solution.
yes.
Stability.
Yes,
so
yes.
Basically, yeah, we know the Intel is doing this for quite a while. So how would you estimate the stability of the reliability of this toolkit so that it's kind of make sure that it works across different platforms as it is claimed to be?
So I'm going to show this with an example, since I am not running it right now, but this is actually an actual example from the code repository. So this is actually a CUDA kernel. So if you use the toolkit, the stability, if you're talking about the stability of the toolkit, so this is just a CUDA kernel, right? Just a CUDA kernel for convolution deep learning operation, right? Which uses, now when you call cyclomatic, right, or DPCT to migrate this, right? It will migrate. So you see something called a CUDNN convolution, forward, something like that. It just a standard migration of your, I would say, semantic to semantic AST from your CUDA to your SYCL. So over here you have the mem copy, right? This is an USM model. If you notice, I had talked about something called as USM and accessors. I had shown the accessor example, but the USM example is there in the codes as well. But this is an USM example where we're using buffer pointers in general. So we are mem copying from the host to the device, just like CUDA mem copy over here. So CUDA malloc in this case. Okay, and you see we are creating a convolution descriptor. Convolution descriptor over here is also getting created somewhere. Yeah, this one, output dimension. And over here we have the async convolution forward, which is almost similar or 100% similar to this CUDA convolution forward. So it is just like a 1:1 mapping of all the APIs. That is where the stability of the DPCT toolkit comes into the picture. When you have a CUDA code, you have something called as -- query mapping. Okay, that is an additional attribute if you want to have experimental features. Let's say some experimental features from CUDNN, some from parallel STL, some from 1TBB, right? If you want to have that, you can add that, right? But by default, the standard DPCT has all of them covered. Okay, you are going to get a perfectly migrated code in general. Just an example of this use case, but yeah.
Abhilash, I'm terribly sorry. I have another questions, but I think we are out of time. So let's maybe take a pause and go to discussion later. But at the moment, I would like to thank you and thank all who listened to us. Yes, and thanks. And I think that's all for this.
Yeah, spasibo, C++ Russia, and thank you for having me over here.